All right. Good afternoon, students. Um, Welcome to another lesson in power systems. I trust you had a good weekend. Trust you had a good weekend. We look to just press on from where we left off last time. Just a couple of things before I get started. You would have known, I assume, I've looked at the assignment, the feedback on the assignment that you did. There are a couple concerns. It is obvious that a couple persons work together. I have no issue with you working together per se, but especially when we're dealing with some of these fundamental topics, I really want to see individual effort so that I can determine early out the level of understanding that's within the class. So having worked together, that shields for me or prevents me from having a full picture of what is happening, and as I said before, the level of understanding. It is why I know that persons work together is that there were some basic errors that were repeated. In one instance, well, as an example, one of the reactants given in the problem, the actual reactants given in the problem was 0.2, but several persons worked it using 0.1. I therefore would have figured that so many students would not have had, issues in terms of mistakenly writing 0.1 for 0.2. There are other calculation errors. Notwithstanding, again, since I don't have a feel of those who really understand and those who don't, I have uploaded the solution. So you can look at that in your own time. All right. For this week, the thought I want to share, I know I didn't share one last week or the week before. It's not that I'm dropping off a ship, just, things just happen. Fighting the wind will not always bring change. Sometimes we simply need to adjust our sails. All right? Unfortunately, I don't have the author, or I don't have anybody to assign to that as some important author, because this is something I shared with my students some years ago and just thought I would continue to share it. All right. There's a reading assignment that I want you to do. That's the information. There's no need really to write it though, no, because you can look back at the recording to get the information, all right? But it has to do with primarily with transmission lines, their construction, how we determine the parameters. I don't want you to focus so much on the math, meaning because a lot of what is done in terms of determining the resistance, inductance, and capacitance is something that you would have already covered in electromagnetics. So I am not stressing that aspect of it. What I'm interested in is that you understand these parameters and understand how they are used in calculating operational features, so to speak, of your transmission lines. I also have there in the reading assignment a couple of examples. You all have a copy of the text, so, I expect that this will be done. I'm not going to be asking for a summary of this. However, as you know, the fact that I've given you this as a reading assignment means that somewhere down the line, you will be tested on it. All right? Okay. So today, we are looking at polyphase systems and sequence networks. And we want to start by talking about symmetrical components. All right? What are symmetrical components, how we calculate them, etc. So symmetrical components. And in jumping into this, we define or we state this theorem. It's called Fortescue's theorem. And before we look at the theorem, let's just understand a couple of things about a power system. Now, whether in machines or, primarily in machines, we would have spoken about balance systems. And generally speaking, under normal operation, a normal operation of your power system, it involves a balance system of voltages and currents. Now, under abnormal or fault conditions, the system becomes unbalanced, right? And symmetrical component, and by unbalanced, or should I let me start at the top. By balanced, we are saying that the voltages are all dispersed by 120 degrees, and in terms of magnitude, that they are all equal. That's what we mean by a balanced system. And we're talking about balance, so we're talking about three-phase systems. Once it becomes unbalanced, what we are saying is that the angles between the voltages and currents are no longer 120 degrees. So they can, be various angles. And also the magnitudes may also be different. So for Fortescue, in looking at these unbalanced systems and how we go about doing the analysis, Fortescue put forward this theorem, right? And symmetrical components is that mechanism that we use, therefore, to analyze the operation of the system under these unbalanced conditions, all right? So here is Fortescue's theorem. And I want to declare that really and truly it's not 3, but it should be n unbalanced phases. But because we are dealing with a 3-phase system, then we include the 3 here. Because this particular theorem can be applied to any number or a system that has any number of unbalanced phases. Okay? All right, so Fortescue's theorem. It says that 3 unbalanced phases of a 3-phase system can be resolved into 3 balanced systems of phases. The balanced set of components being the positive, the negative, and the zero sequence components. All right? So as I was just saying, in your unbalanced system where you have voltages, different values, this with angles varying angles, so the angles are no longer equally 120 to give us the 360 degrees, yes? In those unbalanced circumstances, Fortescue is saying that we can represent the system, yes, by using, or we can resolve the system by using 3 balanced systems. All right. The balanced set of components that we're going to be talking about are your positive, your negative, and your zero sequence. And so we're going to now delve into these 3 sets of components, look at them in a lot more detail, and then hopefully the idea in terms of, how do we analyze the system when under fault or under unbalanced operation, how we go about doing that. All right, so we start by looking at positive sequence components. And positive sequence components consists of 3 phases, which are equal in magnitude displaced by 120 degrees in phase and having the same phase sequence as the original phasors. All right. And the key here also, in terms of distinguishing it, is denoted by the number 1. So that's how we identify positive sequence. So I know you have been using it. For example, in your lab, you would have seen Z1, Z2, Z3, or X1, X2, X3. Those would have been the positive. The X1 would be the positive sequence reactance, or the positive sequence impedance, etc. All right, or susceptance. All right. So, what are the key terms here for positive sequence? 1, they are equal in magnitude. 2, they are displaced by 120 degrees. And 3, they have the same phase sequence as the original phasor. Now, the standard phase sequence, what we are saying is that it would be A, B, C. That would be the phase sequence. Because remember, we are dealing with a rotating magnetic field. We're dealing with a generator. So therefore, it's rotating. But when we use phasors, what we have done is to freeze the voltages in time. Yes. So that's how, that's the concept of phasors, looking at it at a point in time. But we understand that we're dealing with a rotating system. All right. So the phase sequence would be A, B, C. And for positive sequence, it has the same phase sequence as the original phasors. All right. All right. Denoted by 1. All right. What else can we say about this? So let us look at these phasors and try and I'm going to be a little detailed with the positive sequence, because if we understand this one, then the others, won't be as difficult. All right. So positive sequence. Firstly, we want to determine the point at which we'll be observing the phasors. And this is what we're going to now use to say ABC. Secondly, in terms of rotation, we know that positive rotation is counterclockwise, right? So that's the positive rotation is counterclockwise. We all know that. So it means that the phasors are going in that direction. Bearing in mind that where the observer is, it means that if that is my phase, if that is my first voltage or my first phase, okay, and I'm rotating in the positive direction, then the next phase would be B. So it means that B is at that point. Of course, the angle between it, A and B, that would be 120 degrees. So B, remember now we are rotating. So if I am at A, if I'm at the observer point, I'm seeing A, that's the first phasor. B would then be the next phasor that I see. So it means that I am going A to B, and then of course to C. So remember now, the observer is stationary. The observer point is stationary. And these phasors are rotating. All right? This angle would also be 120. This angle would also be 120. So they are rotating, obviously, they're going at the same speed. Yes? And therefore we can freeze it in time, and we are able to look at the three phasors. Any questions? Anything I've said so far that is unclear?
Yes, sir.
Hey, go ahead.
in terms of the rotation, right, sir, is it that the observer is looking just like it is in the diagram, or is it that I am looking forward and the rotation is going counterclockwise?
All right. The observer is stationary. What we are saying is that you're looking at this point. So you're looking at this. Let us say you're looking at that point. And what you're doing is just to write the phase that you see. So as is, the first phase that you're going to see is phase A. So you're going to see phase A. Remember now, they are rotating in the counterclockwise direction. So after A moves, what you're going to next see is B. After B moves, the next one you're going to see is C. The principle of phases is that we freeze it in time, and we are looking at it. But I'm saying to you, you need to always keep in mind that we are dealing with a system that is rotating. The fact that it is rotating is neither here nor there, so to speak, because they are equally displaced in terms of angles. I can freeze it in time. That is why I would have had that. I have these three phases, and I know that they are separated by 120. I could have also had them looking like this. Doesn't matter. They are still dispersed by 120. Right? These angles are all equal. But it's just that I would have frozen them at a different point in time. I could have had them looking like this. Again, all displaced by 120, but just that they are frozen in a different point in time. But this would have been A, B, C in terms of phase sequence. If I was observing it from this point, all right, if that is A, then it means that this is B and this is C because the rotation is in that direction. So I see A, then I see B, then I see C. That's what we mean by phase rotation or same phase sequence. All right? Okay, so that's the positive sequence. The original would have had the phase sequence A, B, C, and for the positive sequence, all equal and have the same phase rotation. Next, we talk about the negative sequence components. Like the positive, the three phases are equal in magnitude. They are also displaced by 120 degrees. Yes? Now, again, from machines 2, how would you reverse the direction of a motor? You have a motor, how do you reverse the direction?
You swap any two wires.
You interchange
You change polarity, sir.
You interchange any two phases, as somebody said wires, right? That's what you meant.
Yes, sir.
Okay. All right. So you just interchange any two phases. All right. Now, if you interchange those two phases, then the motor will change in terms of the direction. All right. Now, if I interchange two phases, the phase rotation would now be what? If it was originally A, B, C, what would be the phase rotation? If it's the opposite. Given that I have interchanged any two, in this case, let's say we interchange B and C. Come on, I just gave it away. What would be the phase rotation?
ACB.
ACB. All right? So that would now be the phase rotation. Okay? So that is what we mean that for the negative sequence, the phase sequence is opposite to that of the original. So this is the opposite to this. So that's your negative sequence. Now remember, I use the motor from an illustrative standpoint. Okay? Now, within your system, it's not that the generator is now going to change direction. We're still rotating in what direction? What direction do we rotate? It's positive rotation.
Anti-clockwise, sir.
Counterclockwise. All right, so we're still going counterclockwise, but the phase sequence is ACB. So in terms of the phases, all right, if I'm still at A, or if the observer is still at that position, it will see A, then C, then B. So that is the opposite phase rotation. All right, for as described for your negative sequence component.
Sir, you can go back to the previous slide for a quick second, please.
Let's wait until everybody's finished with this.
Okay.
You mean the one for the definition of negative?
Yes, sir.
All right.
This one.
Everything that you wrote down for positive remains the same, except having an opposite. So having a phase sequence opposite to that of the original.
Yes, sir. I just want to know what it is denoted by.
Number two.
Okay, thank you.
You're welcome. All right, and that is shown here. So for the negative sequence, it's denoted by 2. All right? Does everybody have this? All right, now, finally, for the zero sequence components consists of 3 phases, sound familiar, equal in magnitude. However, in this instance, there's 0 phase displacement from each other. So in other words, the 3 phases which are equal in magnitude are all in phase. So whilst the positive sequence and the negative sequence are displaced by 120 degrees, the zero sequence, there's no displacement. For use of a better word, they are one on top of each other. All right? All right? In terms of representation, all in phase. Okay. So let us just look at those three diagrams, those three phases that you have drawn, and we are going to apply some math to it. All right? So if we consider just the voltages, so let's look at the voltages first. Go back to what Fortescue said. Fortescue said that the unbalanced phases of the three-phase system can be resolved into three balanced system of phases. Yes? And the balanced set of phases being your positive, your negative, and your zero. So VA, VB, and VC are these unbalanced phases. Yes? And we are saying that we can represent VA by these three balanced phases. We are also saying that we can represent VB by these three balanced phases. And also, we are saying that we can represent VC by these three balanced phases. All right? So each unbalanced phasor can be represented by its zero sequence, its positive sequence, and its negative sequence. All right, now, in terms of relationships, remember how we defined the zero sequence? We said they were all equal, no? And for the positive and the negative, there was a 120-degree displacement with those phasors. Okay? So we're going to use those relationships in simplifying what we have before us. Are we finished with this? All right.
Yeah.
So for the zero sequence, we know that they are all equal. Yeah. Now I want you to just write down the others and then I'll explain it. We are introducing A. I'm just telling you that the operator is defined by this, right? A is equal to 1 at angle 120. So if we multiply anything by A, all we are doing is displacing it by 120 degrees. All right? So we won't be changing the magnitude, we're just shifting its position. And here we have the relationship between the positive sequence components and the negative sequence components. All right? Now, let us see how we go about establishing that VB1 is equal to A squared VA1. Do we have all these relationships?
No, sir.
So let us start with the positive sequence values. And we're looking now at VB1 and VC1, okay? So let's look at the positive sequence. This is VA. The question is, how do I move from A to where VB is? That's the question. All right, so how would I shift this phasor from where it is to where B is, bearing in mind that we are going in a counterclockwise direction? And simply, what that means is that VB1, to get to VB1, we'd have to go through 240 degrees. So that would be A squared, right? So A squared would be 1 at angle 240. All right? And for VC, what we're saying is, how do I get to VC from A? And that one would move it through 120 degrees. So I would shift A by 120 degrees in order to get it to VC. All right? And the same reasoning would be applied to the negative sequence. I'm at A. How do I get to B? I shift it through 120. So that would be A. All right? From A to C, I would shift it by 240 degrees, which would be A squared. Nice and simple, all right? Anybody uncomfortable with that? All right.
Sir, question.
Yes.
So you're saying that A is practically 120.
I'm sorry. The thunder disrupted. I didn't hear clearly. Go again.
I'm saying that A in this case is just a 120-degree shift, right? As stated earlier.
Yes. Yes.
Right, sir.
So you multiply anything by A. A is 1 at 120. All right. So all you are doing is shifting by 120 degrees. All right. Okay. So I can now rewrite the equations I had earlier. All right. These are the equations I had. So I'm now going to substitute for VB1, VB2, VC1, and VC2. All right, those are the substitutions I'm going to make. So I can then have, and of course, VB0 and VC0. So I can then have a series of equations of values in terms of VA. Obviously, I mean, you have enough networks experience to know where we are going with this. All right. So those are my components in terms of VA. Okay, now, once we have this, obviously, you know, we can put this in matrix form. Right? So we can put this in matrix form. And in doing so, that's it. And this we call our T matrix. Now, folks, I think by now, I mean, most of you, I would have, well, not most, that's not true. I was about to say most, I had you in networks 1, but that's not true. Anyway, it's not germane to the point I want to make. I think I've taught most, if not all of you already, and I have been encouraging you to invest as engineering students in a good calculator. All right, and this is where it starts to become even more relevant. For me, I just store. I store this T matrix. When I'm using matrices on my calculator, there is matrix A that I do not alter because that matrix is my T matrix. I don't, so anything I'm doing, I'm using B to wherever it goes. But I will never adjust matrix A. All right, because that is the T matrix. And once you're doing power, anything related to power, you're going to be using that matrix. All right, so it's a good practice. And this is one thing that you can store in a calculator and feel happy that you can walk with it into an exam. All right, so a word to the wise is sufficient. So you want to store and have this T matrix available. And so TA, or T rather, times our 0, positive, negative. And please, it is no shame that you may forget it. I'm saying that because I have forgotten it a couple times. So I'm saying to you, bear in mind that we go 0, 1, 2. Right? Sometimes just in getting the work done, you know, you may use the first one as 1. Of course, this is giving us the unbalanced values in terms of the sequence values. All right? Which is what you would have been after if you were then analyzing the system under fault. Right? You want to know what the current would be in a phase, in a line under fault, or you want to know the voltage on the line during a fault. Okay? And so what you would be using to calculate that are the sequence values. So this is the typical manner in which this would be applied. However, for the purpose of trying to understand what we are doing, I'm going to give you the inverse of T. All right. So this would be inverse T. All right. So it's 1 over dt times the adjoint. Remember those fancy things. All right. And note that the only change here, is that you interchange the A and the A squared. All right. So from the T, and if you don't remember T, just remember that the first one you write is A squared. All right. So the inverse would be A squared, and A squared A. 1/3 of that. All right, so in other words, if I want to find the symmetrical components, or rather the sequence values, It should be sequence. All right. They are symmetrical, but yeah, I will make the other way there. All right. Everybody has this? Are there any questions? Are there any questions? All right, we're going well.
Sir, question.
Okay.
Sir, something is not really clear, sir.
Mm-hmm.
It start subbing the values for the values of VA, VB, and VC, sir.
Mm-hmm.
Probably can go over that just a little bit, sir. I thought I missed something, so I'm trying to see what I missed, sir, if possible.
Okay. Let's start at the beginning. Do you understand what we meant by what Fortescue meant? You understand that?
Yes, sir.
All right. So Fortescue is saying to us, I'm repeating it because it will help to provide some understanding here. Fortescue is saying, when we have an unbalanced system, right, we have three unbalanced phases. I know add to that unbalanced situation, yes, occurs when you have a fault on the system. Because under normal operation, they will be all balanced. Under normal operation, they will all be displaced by 120. Magnitudes are fine, are the same. That's under balanced condition. Once you have a fault on the system, whatever that fault is, right, we are not concerned just yet as to the type of fault that we have to deal with. All we are concerned with at this point in time is that you have a fault, all right? Once you have a fault, the voltages and currents will no longer be balanced. In other words, they'll have different magnitudes and the phase between them will change. And Fortescue is saying, you can determine the magnitude of these unbalanced phases, which will be given by this. Those are your unbalanced phase voltages. Yes? You can do that by using these balanced phases that we call positive, negative, and zero sequence. All right? And if you use them, yes, then you can add them up, just like this. You can add them up and get your VA, your VB, and your VC. Let us look at an example. Let's look at an example. All right? Let's look at an example. Take this example. Take this example. What you need to bear in mind, students, is that I am telling you here that these are the IA and IB, IA, B, and C. I am telling you that these are the unbalanced currents. All right? When you have a fault, or let me put it the other way. In determining what the current is on the fault, I would have to use the sequence currents. You with me? I wouldn't have known these values. I would have to use the sequence currents in order to find these values. The 150, 180, 200 at these various angles. All right? And that's where we are heading next week when we look at fault analysis. How do we use all of this information to determine the currents and voltages that occur when my system is under fault? All right? All right. Do we have the question? Shall we move on?
No, sir, just a second. Okay, sir.
All right. So what we have here, going back to the example, what we have are the unbalanced currents and or voltages. And by the way, we said earlier that what applies to voltages also applies to currents. All right? Okay. So as a reminder, what we are trying to find are the sequence currents given the unbalanced phasors. And we use these relationships at the end. And let me not beat around the bush. Although I may go through this example now for you, just get to the point where you understand that you will have to do this calculation in an exam setting. All right? So you'll have to do this within that period of the 2 hours. All right? I can tell you from now, you're going to get a question on this. All right? Okay. So, not what I'm doing now, just to be clear. I mean, anyway. So the first thing would just be to apply the formula. So it's 1/3, 111, 1a squared, 1a squared, 1a squared a, right? Times our currents. And I do not want anyone to tell me that their calculator can't, they can't put in these angles in their calculator. Even if it cannot, even if your calculator does not give you that flexibility, you still can expand the matrix, right? And work it out longhand, so to speak. Okay. So by having calculated this, we're not going to go through the whole process. And I strongly encourage you to ensure that you go through and do the calculation again on your own and make sure that you can do it. All right. So we'll get the IA0, 1, 2. But as we indicated just now, yes, we have this relationship this is the relationship we have for the voltages. What we're saying is that the same relationships would exist for the currents, meaning that IB1 would be equal to A squared IA1. And IC1 would be equal to A IA1. All right, that's what we're saying. Same relationship. So we have that relationship already. All right. So we can find IB1. We can find IB2. We can also find IC1 and IC2. All right. And as you can see, all that is happening is that it is being shifted either through 120 or 240 degrees. All right. So I see 1, I see 2, and of course, for the 0 sequence, they are all equal. Okay. All right. So this is what I need you to do. Because we had VIA, IB, and IC. What you now have IA0, IA1, IA2, IB0, 1, and 2, IC0, 1, and 2. You're going to add these three, because remember, in defining these sequence values or components, we indicated that they were all in phase, all right? Which is what Fortescue said, that we can represent this unbalanced system by a balanced series of phasors. Good. So you're going to add IA 0, 1, and 2, and you ought to get back what you got for IA. Same thing for B and C. So you do that in your own time. All right? I pause again. Any questions?
So you can repeat it, this, please.
You're going to add the sequence values, 0, 1, 2, for each phase. So you're going to add IA 0, 1, and 2, IB 0, 1, and 2, IC 0, 1, and 2. And if our math is correct, then the values we had there for IA, IB, and IC, you will get those. You'll get back those. All right?
Okay, thank you, sir.
You're welcome. Which is what Fortescue is trying. Okay, so pushing it out. We want to touch a little bit. Not going to get into the belly of it today, but we want to touch a little bit. This whole business of symmetrical components. All right. Now, symmetrical components, as we say here, are used in the analysis of faulted networks by creating what we refer to as sequence networks. And when you get the link, remember what we just calculated or what we just spoke about, yes? Are sequence currents and voltages, yes? What we have here is that the networks, the sequence networks, will provide us with the sequence currents and the sequence voltages. All right? So our objective here is to be able to develop the sequence networks. And once we have developed the sequence networks, then we can use these networks to find voltages and currents. All right? Okay, so let's move on. So by definition, your sequence networks are single phase to earth. All right, very important. Single phase to earth diagrammatical representation of each of the components in the original circuit. So since I'm going to represent what's in the original circuit, I hope you're, well, I shouldn't say it that way, but I want you to make the link to what we did last week, because if I'm going to represent them, then I'm going to have transformers and all of that. And to get these networks in a simple format where I can go from one end of the network to the next, I'm going to need to put them in per unit. So sequence networks are single phase diagrammatical representation of each of the components in the original circuit. So what I'm going to do now is to look at how we represent each major component in a power system. I took the decision last year not to, because you are not specializing in power, not to ask you to develop your own networks. All right. I will continue that. Yeah. I'll leave it at that for now. But we will have to address that if persons are really interested in power, then we will address that before we delve into protection. All right. So we'll come back to this and show you how to develop your sequence networks. All right. So as I said just now, we need to look at how we represent each major component in the power system, right? And then we get our equivalent network, and then we find our voltage and current. Okay? All right, so we're going to start out by looking at our generators. So for your synchronous generator, where the phase voltage is EA equal EB equal AC. In other words, they are balanced. Yes. And Z1, which is your positive sequence impedance, is equal to X double dash D. Right? So going back to your machines, right? X double dash D would be your subtransient reactance. Right? On the fault, your synchronous machine reactance changes. Okay? So you would have your synchronous reactance, which would be your XS, all right? And then you would have your XD, which would be your transient reactance, and then your X double dash D, sorry, and then X dash D, and then X double dash D would be your subtransient reactance. Now, the subtransient reactance is the lowest reactance that the generator would experience under fault. And the reason we use it for your positive sequence is that because it gives the lowest reactance, it means that it will give the largest current. And we want to look at the generator on a worst case operation. All right, so we want to see the largest current that would flow through your generator under these circumstances. And your negative sequence of Z2 And just as notes here, we're saying that the negative and positive sequence impedances will be had from your manufacturer. Yes. Of course, you can calculate this. Yeah. The zero sequence impedance contains the machine's zero sequence impedance as well as the earth or neutral impedance if it is in the circuit. And let me repeat the second one because it is important. The zero sequence impedance would be involve both the machine's zero sequence impedance, that's supposed to be okay, so it's the machine's zero sequence impedance plus the earth or neutral impedance if applicable. So there may be for whatever reason the need to just earth the generator solidly, meaning you don't have a resistance in the earth path. All right. If you are doing that, then fine, the zero sequence will just be the machine zero sequence. But if I earth it through an impedance, and we can, again, if we, from a protection standpoint, we can talk about the reason for earthing it through an impedance. All right. I think you'll test it in one of your labs. But for now, yeah, just take that, we will have use for it at some point in time. But you'll note it in one of your labs. All right. So in terms of representation, this is how we represent a generator. For the positive sequence network, we have a voltage EA in series with Z1. Now, folks, it's a simple representation, but it is very, very, very important. All right? Now, based on this network, note IA1 is flowing out of the network. IA1 is flowing out of the network. So based on this network, what would VA1 be equal to? What would VA1 be equal to?
So EA minus IA1 times Z1.
All right. So it will be EA minus IA1 Z1. All right. Not a problem. Perfectly correct. So at the end of my positive sequence for my generator, VA1 would be equal to that. For your negative sequence, that's the representation. Again, IA2, like IA1, is flowing out. So what would VA2 be equal to?
So IA2 times Z2.
Not exactly. You want to give it another try?
Negative,
Go again.
negative IA2 times Z2.
Why negative?
So because the VA2 would go against the IA2 like its opposite directions.
Okay. All right. Well, it would turn out to be negative, but not for the reasons you just gave. All right. Now, obviously, there's a current flowing out. Yes. So to represent that, what we have is that the EMF is 0. So it is 0 minus IA2 Z2. All right. But then again, I suppose what
Sir, quick question, sir.
yeah, man, listening.
Yes, sir. Could it be negative because probably you're looking into the circuit from that angle, sir, or from that side of the circuit? No.
No, man. I'm saying what Miss Donna said. I can accept it, but what you must always bear in mind, all right? Don't get well. This representation is correct, but what I want you to always focus on is that this is always flowing out. All right? You will soon see the importance of that. So it's always flowing out. And the same thing for the positive sequence, same thing for the zero sequence, always flowing out. All right? I won't stress you with it just yet. And then for the zero sequence, remember we said that the zero sequence contains the zero sequence of the machine, yes, as well as the earthing impedance if it exists. All right? That is represented as shown. Now let me explain quickly what this means. If you are not given by the manufacturer or you're not given the value in a question, so you're not getting it from the manufacturer or the examiner. All right? It is fair to assume. It's fair to assume that the zero sequence impedance of the machine is anywhere between 0.1 to 0.7 of XWD dash. And how did we define XWD dash? What's the other name for it again?
Transient reactance.
And what is that? What is it? It's equivalent to what?
Right. I think you said the lowest reactance.
No, man, look back at the note you just wrote.
Z1.
Z1. All right? So, if you are not given a value for Z0, either by the examiner or the equipment manufacturer, Z1, you would have been given Z1, but Z0 for the machine can be taken as anywhere from 0.1 to 0.7 of the positive sequence reactance. Are we clear?
Sir, can you repeat that, please, sir?
If you don't have a value for Z0, you can estimate it as between 0.1 to 0.7 of Z1. Because you must be given Z1, you know. All right? But you will not necessarily be given Z0 for the machine. Zn has nothing to do with the manufacturer because you, as the engineer, would have installed the generator and earthed it through an impedance. So whatever the impedance that you insert in the neutral, you are going to multiply it by 3. You're going to multiply it by 3 and add it to Z0 in order to get Z0 for your generator. Again, note IA0 is flowing out. So it means that VA0 is equal to 0 minus IA0 Z0, where Z0 is all of this. All right, so we did say that we're talking about polyphase system. So there are a couple of things that I want to just highlight here before moving on. 413. Whoa. Okay. All right. So a couple of things we want to highlight. So let's take these notes for me. I'm not going to spend a lot of time going through it. I'll just give it to you. You take them. I will move on. All right. But of course, you have to appreciate it. So I want to talk a little about the zero sequence curve, because it may not be something that is readily understood by everyone. Okay. So let's get going. Now, the unbalanced current that flows in the circuit during the earth fault is known as a zero sequence current, or it is the DC component of the fault current. All right. And the other point there, we already spoke to that. Zero phase sequence means that the magnitude of the three phases has zero phase displacement. So one on top of each other. But instead of drawing a single line, we draw three parallel lines. That's how you'll see it represented. It's your choice. However, if you were to use a book outside of the recommended text, a book that may be older, you may see, and it just came back to me, which is why I'm sharing it. You may see A that we mentioned earlier, that 1 at 120. You may see it represented as H. All right, it's the same thing. All right. But you all have the textbook, so there's no need to digress to look for anything else. All right. Now, the figure is coming up after this, so you just take the note. So the three vector lines represent the zero sequence current. And it is detected by adding the vector of the three phases. All right. Now, as we established earlier, yes, IA0, B0, and C0 will all be equal. So we have this expression, but again, we need to now look at zero sequence in terms of different windings, whether we're dealing with a delta or star. right, so as we have already established, the zero sequence current of each phase or of phases A, B, and C equal in magnitude and in phase with each other. Okay? We have already established that. Now it is circulated in the phase windings of a delta connection as shown. All right. So they're circulated in the phase windings of a delta. All right. Do we have this?
Excuse me, sir.
Yes.
Regarding the subscripts for the currents on the delta diagram, I was wondering if the subscript could be explained.
Which ones?
For the currents on the delta.
ICAO?
Right, right.
That's just the, all right, fair enough. So of course, IA0, IB0, IC0, these are all the zero sequence that will be flowing in each phase. All right. So that's supposed to be AC0, BC0. The two CA0 and BA0, interchange those.
Okay, sir.
I'm assuming that was a confusion. We had CA on the BA side and AC on the AB side. All right. What we do here, we can apply Kirchhoff's law, current law. So let's say, well, in this instance, we applied it first to node A.
So, sorry to interrupt, sir, but for the part where the current is flowing from C to B, why you have BC, sir? IBC0 instead of ICB0.
If you note at the bottom, I did not insert it. I used answer the source at the bottom. So they would have had that error there. But the key thing, really, and it's a good thing you pointed it out, I need to, improve my source. The key thing is just to show that you do have the current circulate, the zero sequence current circulating to each of these windings. Right?
Okay, sir.
Just trust me that it is not critical to what I'm about to say.
All right, sir.
All right. So if you applied the current law, to node A. All right. Because remember, we had already established that they are all equal and in phase. All right. So the current coming in, or the resultant zero sequence current in phase A. Yes. Let's go back to it. So this plus that's the current going into that node. All right, would be equal to the current leaving the node. Okay? Which is what we have here. Current entering equal current leaving. All right? So IA would therefore be equal to AB minus CA. But we said that they were both equal. And equal to I0. So it means that IA0, or in other words, the current flowing into into that phase. Yes, would be 0. And if we applied the same principle to the other two nodes, the nodes B and C, and if we apply those to nodes B and C, sorry. Where am I? All right. If we apply that to the other two nodes, then we'll also get 0. And the fundamental point that we wanted to get to is that there is no zero sequence current present in the delta connection. All right. So what you would have is a circulating zero sequence current.
Excuse me, sir.
I'm listening.
So is that one of the reasons why the delta I would say the delta network is more preferably used in like on the light poles and stuff like that?
All right. in a power system, the delta is primarily used to sectionalize the network. All right. What does that mean? It means that it will not allow zero sequence to flow from one part of the network to the next. So in the case of what's on the light pole, there are different reasons for that. For example, that is how we would get our 110, 220. Because you would be using a tapped delta
Yes, sir.
winding for that. You wouldn't be using that. But again, it's primarily sectionalizing the network. Right? The question you ask, if that is why we use it, it may be one off, but it's not necessarily
The only
the
reason.
primary, yes.
Oh, all right. Okay, sir. Thank you.
You're welcome. All right. Now, there is no return path. And since he brought up the question, when you the generator transformer, right? Although your generator, you usually connect your generator a star, right? You need that earth point. But the generator transformer would then be a star delta transformer for the purpose I just mentioned. You have the star side that facilitates your earth fault, but the delta separates the generator from the rest of the network. So therefore, if you have a fault on the network, the zero sequence from that fault, yes, would not then be transferred to the generator. So the star delta provides that separation. Again, there are other implications of using a star delta, but I just mentioned that in light of what was just asked. Right? All right, so in terms of how we then represent a zero sequence, right? It'll be shown as an open circuit, because if we are saying that the current is zero, yes, and we know that there is a voltage on the system, okay, there's a voltage on the system and the current is zero, then technically speaking, it means that the impedance is infinitely large, right? And so in terms of representation, all right, I feel a little pressured because I didn't realize that time had slipped away from us. All right, so let's just speed this up a little. We have this. So in terms of representation, we'd have that as an open circuit. Okay. for your ungrounded star, for your ungrounded star, as we had indicated as with the delta, all right, similar to what we had with the delta.
So 30 more seconds on the last side, please. All right, sir.
All right, good.
Excuse me again, Dr. Isaacs.
Mm-hmm.
So is it safe to say, similarly to the star delta transformer, is it safe to say we could use a star with one side ungrounded of the star in the separation of the, to get rid of the zero sequence that could come back to the generator?
I hope you'll be doing protection in January.
Okay, sir.
Because you are perfectly correct. The impact as delta is quite similar to an ungrounded star. And so no zero sequence will flow with either a delta or an ungrounded star. All right. The simpler way to put it, really, the simpler way to put it is that zero sequence will only flow with a grounded star. That's a simpler way to put it, because all others will not allow that to happen.
Okay, sir. All right, thank you. Yeah.
All right, so for your grounded star, which is what we were just alluding to, for your grounded star, all right, okay.
So you can go back for 5 seconds, please. Okay, sir.
One, two, three. All right. So what we are showing here is that the zero sequence will flow only with a grounded star network. Now that becomes important. And we have been, unfortunately, I didn't get the name of the person who was asking those brilliant questions, which I really appreciate. The transformer, in terms of how we treat with it, I'll put it there that it is the most difficult component within your network in terms of representation. Can we talk about how you represent the generator? I've gone through this or given you all of this information regarding the zero sequence, yes? Because when it comes to the transformer, it is not as straightforward as we had shown with the generator. We had established the generator, the zero sequence was Z0 plus 3Zn. All right. For the transformer, we will have to look at how the windings are connected. All right. What windings we have and on what side it's connected, whether it's on the primary or the secondary side. All right. Okay, so for your transformer, your transformer is a static device, and therefore the negative and the positive sequence impedances will be equal. All right. So for the generator, the difference was due to the fact that you had a rotating system or rotating device. For your transformer, positive and negative are equal. The challenge, as I mentioned briefly just now, the challenge is in determining your zero sequence network, because the zero sequence is going to be impacted by whether you're dealing with a star winding or a delta winding. All right? Now, the positive and negative sequence networks are affected by the 30-degree phase shift between the primary and the secondary windings. But I'll tell you for now that at the undergraduate level, some persons may say that I ought to, but I usually allow students in their calculations to neglect the phase shift that is produced by the in the two windings. And you are familiar with this issue of the phase shift between the primary and secondary for your transformers. Again, don't shoot me through the computer, but again, that's from machines. All right. So we must also know that the zero sequence currents cannot flow unless there's a path to ground, as we just explained. Yes. So the only winding that will allow zero sequence to flow would be your grounded star. All right. Otherwise, it won't flow. So if it's a delta winding, you will not have zero sequence. If it's an ungrounded star, there will be no zero sequence. So the only winding that will allow zero sequence would be your grounded star. All right? And to make the determination in terms of the zero sequence for your transformer, yes? So for the zero sequence for your transformer, we use a network and we say here, if zero sequence can flow, yes, you close contact A, and if zero sequence cannot flow, you close contact B. There seems to be a couple persons who are having some internet issues. They are going in and out. Who is that? Who is being affected?
Me.
Who is that? Lamanja?
Yes, sir.
Okay, okay. I hope you haven't missed too much. All right. So, so this is the figure that we use in determining your zero sequence. So if zero sequence can flow, we close contact A. If it can't flow, we close contact B. So in other words, this transformer, if we were to close contact A, we would say that on this side, we have a grounded star, and on this side, we either have a star or a delta. That's all it means. So this winding, this first winding would be star, the second winding would be grounded star or delta. You understand that?
So the second one needing grounded star and ungrounded star and delta.
The first one, if we close A, it is a grounded star. If the other one, it's an ungrounded star or delta.
All right. So.
All right. Okay. So next we look at the transmission line. For the transmission line, again, static device, so Z1 equals Z2. And in your reading, in the reading activity that I gave you, all right, you will also note that your Z1 and Z2 would be equal, what we have here, ZS minus Zm. These are self and mutual impedances. And Z0 would be equal to Zs plus 2Zm. All right. So in effect, what we're saying here is that usually, not usually, your positive and negative sequence are smaller than your zero sequence. So you can, keep that in the back of your mind. So if you see values that are not true to what we have here, because if it's the same line, the self-impedance and the mutual impedance must be the same whether we are calculating the zero sequence or the positive sequence impedances. And Z1, so if I give you Z1, it means that you also have Z2. Yes. So these are little things, the persons had gotten into this habit of telling me what was left out in Network Studio during the summer. And I smiled because people left out a whole question because something was left out. Get used to it. All right? Some information you'll be given, some you will not be given. But you need to understand that based on what you are given, you can derive the other body of info. All right? So that's part of testing your understanding in terms of power systems. And then finally, we go to static loads. And of course, loads can be star, they can be delta, they can be grounded star, they can be grounded through an impedance, etc. And we have to look at how we treat with all of these. All right, so for static loads, and while we go through static loads, I'm going to ask that you, when I go to the diagrams, I'm going to ask that you answer to your names. I did not take my register last week, but it is something I have to do, or I ought to do on a weekly basis. So please respond to your names. Also, there are some persons, I have 54 persons that have signed up to the module. However, for the last 2 activities that I gave you to do, only 44 persons responded. If you are aware of persons, with whom you are associated, just ask them kindly. I would have imagined this is the appropriate thing to do. Just ask them if they are withdrawing from the module or if they have the intention, just to indicate via email, so we can remove them from our register. All righty. So let's see who is not here. So for static loads, are we finished with this? For static loads, all right. So the first one would be an ungrounded star. The next one, of course, would be a solidly grounded star. Right. So if you note in this one, there is no zero sequence. Of course, in the solidly grounded star, we have zero sequence, correct? So please, just respond to your name. Adams.
Present, sir.
Allen, Chavez, Allen.
Yeah.
Barrett, Shake. Barrett? Miss Barrett not around. Okay. Blake, Rajay?
Present.
Blake, Tevon?
Here, sir.
Brown, Garrett? Brown? Bruce? Buckley? Buckley? Burns?
Here, sir.
Campbell?
Present.
Chambers? Daniel? Daniel, okay. Scott? Copley? Copley? Crossdale?
Here, sir.
Daly?
Yes, sir.
Down
Here, sir.
the places. The places. Dwyer.
Yes, sir.
Ellis.
Here, sir.
Ferguson.
Here, sir.
Finley.
Here.
Francis. Adrian.
Here, sir.
Henry. George. Henry, that is. Zavina.
Yes, sir. I'm here, sir.
Hewitt.
Yes, sir.
Jeffrey.
Here, sir.
Johnson.
Here, sir.
Kamika. Jamal. Kamika. All right. Carr.
Yes, sir.
All right. Let's pause there. Do we have this? Do we have everything on this slide?
Yes, sir.
Sir, could you go back for about 2 seconds, sir?
No, let me go to the next slide and then we can go back to that.
Okay.
All right. And then what we have here is that this is now a grounded star through an earthing impedance. And just like the generator, we will have 3Zn. All right. So 3Zn would be added to the overall zero sequence impedance current, impedance, right? So the overall zero sequence impedance for your static load, that is earth through an impedance, will be 3Zn plus Z0. And then, of course, for your delta, you'd have a circulating current. Okay, so let's go back to the register while you draw this. Leon, Ishmael,
Here, sir. Here, sir.
Louis, Rajiv. Louis? Okay. Mason? Mason? Merchant? Montague?
Yes, sir.
Mundell? Norton?
Yes, sir.
Phillips?
Here, sir.
Porter? Ramsey? Ramsey? Ready? Reed?
Here, sir.
Sorry, Christoph?
Present, sir.
Dario? Dario?
Oh, sorry, sir. When they said read, I thought they was talking to me as well, sir.
Oh,
But
so
I'm here.
both Chris? Okay, Dario. All right, cool. Rose, Colin. Russell, Kamala.
Here, sir.
Shand,
Here, sir.
Shirley. Shirley. Sinclair.
Yes, sir.
Smichael.
Here, sir.
Smith, Rajiv.
Present, sir.
Thomas.
Here, sir.
Oh, come on. Venna.
Present, sir.
Okay. Have I missed anybody?
Yes, sir. Copy.
No, man, I called a long time, but I got no answer. And then we have Nicholas Watson. Watson. Williams. Patrick. Zheng.
Sir, I think he's typing in the chat, sir.
Okay. Okay. All right. Okay. Wow, it's 5 o'clock. That's oh. All right. So when we meet again next week, we will delve into fault analysis and look at how we use everything that we have discussed this afternoon. How we use all of that in analyzing faults on our power system. All right. Have a good afternoon. And please, 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 I know I said it at the beginning of the module, but I'm saying it again. I can't say it enough. In doing your labs, please treat it as if it's a model power system and that you're not simply going through a computing exercise. All right? Some of the material I have given you, I've put in the reading assignment may be relevant to your lab. All right? So,
Sir?
yes, Ms. Downer. Yes, Ms. Downer, I'm listening.
Sir, is me saying with sir?
Oh, yes.
In terms for the lab, sir, based on the guideline you gave us on the lab report, sir, the methodology, sir, I'm not sure how you want it structured.
Methodology?
Yes, sir.
What mark you get for that?
I don't sure you yeah, I'm not remember, I'm not recalling seeing a mark for it, sir.
Because I give you a lab sheet, you don't need a method.
Okay, sir. Thank you, sir.
All right. What I've stressed, what I've put there is what I'm marking. So I'm marking your theory. I'm marking your results. I'm looking at your discussion or analysis, and I'm looking at your conclusions. Method is something you're doing first year. I don't have time for that.
Okay, sir. Thank you.
All right, good. All right, that's it. Have a good one, and enjoy the rest of your afternoon into this evening. All right, goodbye.
All right, sir.